Hello, and welcome to a series of talks about how views about the nature of light have influenced theories about the nature of the physical world, what we can know about it, and how best to describe our knowledge of the physical world. The plan so far, if I can get through it all, is to give a series of 6 talks. Today's is just going to be an introductory talk in which I hope to convince you of the mysterious nature of light. Then in talk 2 I'll look at the ancient world and what assumptions were made about the nature of light in Euclid's systematization of geometry, and how his method influenced the development of science both in the 17th and 18th centuries and through to the 20th century. In talk 3 I'll look at classical physics derived from the work of Isaac Newton, what assumptions that made about the nature of light and how we see the world. Then in talk 4 I'll come into the 20th century and look at how Einstein saw that the time lag between events happening and observers observing them meant that different observers had different perspectives on events happening in the world and would have different descriptions of them, and how that problem could be resolved to produce a consistent description of the world that everyone could agree on. That will be talk 4. Talk 5 will be about how Einstein's work led to the realization that light didn't always travel in straight lines. It could, the path of light could bend, and how that threatened to destroy one of the key assumptions that underlay classical physics, and how that problem was resolved. And then in the final talk I'll look at how Einstein built on the work of Max Planck, and together with others like Niels Bohr, Erwin Schrödinger, Werner Heisenberg, others, developed this theory that light is transferred between charged particles in packets of energy. Packets of energy are called quanta, and packets of specifically light energy we now call photons. So how the theory of photons and quanta developed will be the subject of the final talk, talk 6, if I get that far. Today I just want to concentrate on why light is such mysterious stuff. It seems such a commonplace, everyday thing. I mean, we see everything we see in the world every day is because of light, so we experience it every day of our lives. We think it would be the most normal thing imaginable. Why should it be mysterious? One strange, almost paradoxical thing about light is that light is the cause of us being able to see everything, and yet we don't see light itself. Light is invisible. We see objects in the world because light is reflected from those objects into our eyes. Our eyes detect the light that's arriving there, sends a signal to the brain through the optic nerve, and the brain then interprets that information to give us our picture of the world. So the brain presents us with a picture of the world, but the brain doesn't show us light, which is what carried the information into the eye. To make this point maybe a bit clearer and more concrete, imagine you're trying to catch a ball. I'm not saying this is you, but just for example, you see the ball because the sunlight bouncing around everywhere, being reflected off everything in the world. Some of that sunlight is reflected off the ball and enters your eyes. That light is focused by the lens onto the retina at the back of the eye. That light energy is absorbed by the retina, and that causes the retina to trigger a signal which goes to the brain down the optic nerve. The brain then takes that signal and interprets it. It draws on information stored in the memory to try to identify what the mysterious object is. In this case, it's a ball. You have memories of balls in stored in memory, so you recognise it It then also tries to do calculations as to where is it, how far away is it, how fast is it moving, and after all this calculation, that information is pushed into the conscious mind as seeing the ball. I've said that we don't see light itself. Some people might object and say, well, the very background to these slides shows a shaft of light cutting through the darkness. Isn't that seeing light? Well, not really, because what is happening here is that the air is dusty and tiny particles of dust suspended in the air. Each particle just reflects light into our eyes. That light is detected by the retina, triggers a signal to the brain, and the brain sees each point of light reflected from the dust and projects into consciousness this image of a shaft of light. But what we're actually seeing is the dust. If the air were completely clean and there was nothing to reflect the light, we wouldn't see any shaft of light. What we're actually seeing is the dust. So the moral I want you to draw from this first part of the talk is that the eye detects light. The eye is the sense which detects this light energy falling on it, but it's the brain which generates the images that we see. So the eye merely detects light, the brain sees objects in the world, but the brain doesn't see light. Light carries information from the world into our eyes. There it's detected by the retina. That information is processed by the brain. Light causes lots of other changes too. Light from the sun warms the earth, drives our weather systems, enables green plants and blue-green algae to grow, and from that all other living things in the world can have life. So light causes lots of things to happen. Physicists have a term for that which causes things to happen. Something which is capable of driving change, causing things to happen, is called energy. So light is a form of energy. But there are many forms of energy. Light is a specific form of energy. It's referred to as electromagnetic energy. Now, you probably know that the material world around us is made up of atoms, tiniest particles of things, and the atoms themselves are made up of smaller particles, some of which are electrically charged. So if we look at a typical atom, and the way we picture it now is most of the mass of the atom is concentrated in a tiny core at the centre, which you call the nucleus. And the nucleus is made up of heavy particles, some of which are electrically neutral, called neutrons, some of which bear a positive charge, which we call protons, and then the vast bulk of the space of the atom, 99.999% of it, is swept out by very light particles inside them, not heavy, called electrons. The electrons are negatively charged, they're pulled towards the nucleus, but they kind of spin around it, sweeping out the volume of the atom. Now, electrically charged particles exert electrical forces on each other. Particles with the same charge, same sign of charge, will repel each other. So two negative charged particles will repel each other, two positively charged particles will repel each other. Particles with opposite charges will attract each other. A negative and a positive particle will attract each other. When particles are moving relative to each other, there's an additional component to the force, which we call magnetism. So electricity and magnetism are both really forces which charged particles exert on each other. So physicists now tend to just talk about electromagnetic forces. They lump them together. And light is the energy we get from electromagnetic interactions. It's the energy that causes electromagnetic interactions. sometimes modern physicists will show this in a diagram. It's called Feynman diagram. Here's one that shows two electrons interacting. One electron's moving up to the left hand side of the diagram, another one is moving at the right hand side of the diagram. The two electrons repel each other, so they try and move away from each other, and that interaction is described as taking place because of energy which is exchanged between them in the form of electromagnetic energy. So this is what light is. Light is electromagnetic energy in transit between one charged particle and another. It carries energy between one charged particle and another. So light is produced when one moving charged particle loses energy. That energy seems to move through space. I'll come to talk about that a little bit more in a minute, until it's taken up by another charged particle which gains the energy. So light is electromagnetic energy in transit from one charged particle to another. Let's emphasize this point again. This is you. I'm sorry, I'm not a great artist, so I can't guarantee this is an accurate representation, but you are looking at the North Star, Polaris, the pole star. The way we describe this in modern physics is that some light energy is being emitted by the North Star. This comes about because the star is very hot and atoms in the star are colliding into each other with great force. During those collisions, electrons in the outermost part of the atoms gain energy from the collision, and then they quickly lose the energy again and fall back to their original state. But as they lose the energy, that energy is emitted into space as light, as electromagnetic energy. That light travels through space. In fact, it travels quite a long distance through space, some 3.5 quadrillion miles, 3.5 million billion miles. It takes it over 400 years, so it's some 433 years later. This energy, which has been lost by electrons in the star, enters your eye. It's focused on the retina. It's gained by electrons in the retina, which now become higher energy electrons. This causes the retina to change shape and trigger a signal which passes down the brain. The brain then registers in your conscious mind there's something bright in the sky, and you see the star. So something that's happened in a star 3.5 quadrillion miles away, 433 years ago, has affected the electrons at the back of your eye, in your retina. Isn't that miraculous? Don't you see? That's incredible. Something that happened in a star 400 years ago, 3.5 quadrillion miles away, has exerted a direct influence on the electrons at the back of your eye. That electron, that energy which the electrons in the star gave up, has been transferred to electrons at the back of your eye. Now, what we know about this process is what happened at the end. We know that light energy entered your eye, triggered the retina to send a signal down to the optic nerve to the brain. Modern electromagnetic theory tells us that that energy started in the star when electrons in the star lost energy. So we know the beginning and the end of the process. What's mysterious is what happened in between, because we don't see light. We know something happened in the star, something happened in your eye. But what happened across those 3.5 quadrillion miles that took 433 years, that process is something of a mystery. We don't see it. It's invisible to us. It's a bit like when you pay for something you buy from a shop using a credit card. You use your credit card, money mysteriously disappears from your bank account, the same amount of money appears in the shop's bank account, but this doesn't happen. Nobody has to go to your bank and pick up a bag of money and physically carry it to the shop's bank. The way the money gets from your bank to the Shops bank is invisible to you. You don't see it. I'm not saying it's magic. Obviously, it involves computers and signals, so on, but it's invisible to us. We don't see it happening. We see the effects. We see where the money comes from. We see where the money ends up, but we don't see the transfer itself. So that process by which the money is transferred from your bank account to the Shop bank account, that's hidden from us. In the same way, the way energy was transferred from the pole star into the back of your eye is something of a mystery to us. We don't see that happening. It's what Newton referred to as action at a distance, in this case, a very great distance. And Newton himself referred to these sort of actions at a distance as occult processes. He didn't mean they were magic, he just meant that they were hidden from us. We know what happens, but we don't see the way it happens. We know energy comes from the star into your eye, but we don't see the process by which it happens. A couple of other points before I finish. Light obviously carries information about the outside world into our brain. In another way, it carries information in a rather like a modern computer transmits information, in the sense that a modern computer encodes information in binary code, that is a sequence of ones and zeros, and in the computer this is done by a series of switches. So if the switch is closed, current flows, so that's on, equivalent to 1. If the switch is opened, it's off, and no current flows, and that's equivalent to 0. If we think of the electrons in the star, when they have excess energy, they're switched on, if you like. They can be represented by 1. And then when they lose energy and go back to their original state, they're switched off again. But that energy transmits across space, and 433 years later, electrons in your retina gain the energy. So in a sense they're then switched on. So they've gained a unit of information. So in a sense, light it's not only energy, but information has been transmitted from the pole star to your retina in a digital form. And finally, I use the word light, and I've identified it as being electromagnetic energy. In fact, electromagnetic energy covers a wide spectrum, from very low energy electromagnetic energy in the form of radio waves, microwaves, up to extremely high energy electromagnetic energy in the form of gamma rays. The human eye is only sensitive to a tiny set of colours in the middle of this range. So what we call visible light is just this tiny part of electromagnetic energy in the middle. So our eyes aren't sensitive to see ultraviolet rays or X-rays, even though they can damage us. In other words, we don't see them, and similarly we can feel the heat from infrared rays, but we don't see it. Our eyes don't detect it. Similarly, our eyes don't detect microwaves or radio waves. But I shall use light to mean any form of electromagnetic energy. So I'll use it for the whole spectrum, not just the stuff we can see. Finally, summary. Light is mysterious because although it enables us to see everything else, it itself is invisible. The eye can detect light, but the brain doesn't see it. The brain uses light to create the images we see of the world around us, but the brain doesn't see light itself. Light in modern physics is described as electromagnetic energy being carried from one moving charged particle to another. We can see the beginning and end of this process. We can see which charged particles are losing energy, we can see which charged particles are gaining energy. But we don't actually see light itself, so we don't see light in transit. We don't see the energy being transferred. How people have tried to understand this mystery is going to be the subject of the remaining 5 talks, which I hope to give. If you managed to listen all the way through this, congratulations. I'll try and prepare the next one.